Okay, so record is on here. Here soon. Okay, so let's test the voice and the sound and the picture. Great. Okay. So, record has started here also as well. So, good afternoon. So, sorry for the late start, but I had problem with the train as always. But we are here. So, I uploaded the materials for the last lecture to my module. I also modified it. I added some extra image and slides. I hope they will help. These small videos, I have to talk about them. I hope you will enjoy them. And okay, I will update these slides as well and erase typos like homework number 1, but the homework number 1 is coming soon because we finish the annex and you will have one homework from 1 week 1, then the next one after annex. And I still don't know when I will leave. Oh, it's full of typos. Oh, great, it was too late. Okay, because of previous experience, I told you third time and last time the requirements of this course. So there are some official and I have some other. In theory, you should be here and I should write down everything. Can I help you? No. Great. But I don't want to do this. You will have assigned homeworks, not 6 but 5, and not 4 but 3 are obligatory to do. The others will provide you extra points in your midterm exam and your exam. There will be one midterm exam on the last week during the time of the lecture, and practice, of course, you will have 3 hours to complete. And you will have a possibility to retake it if it's necessary. And you have to write 40% for the signature. Okay, I told you the extra credit. And you will have an exam. If you go to the GitHub and find my previous courses exams, it's simple. There is no something preliminary exam or whatever. You will have 10 questions. You answer the 10 questions. Usually I ask short expressions, but sometimes I will ask essay. Typically, I talked about Fourier transformation last time. I don't expect you to apply it. Don't worry, within a few months you will be experts from other subjects, but I will ask, for example, what are the Fourier transformation, what is discrete, what is continual transformation, what do you do, what practical application do you have? This is an essay question from exam. for example. Or I will ask you, what is the definition of wavelength, for example, or what is the definition of mass point, or something like this. If you prepare, then you will pass, and I hope you will get a good grade. Additional stuff, unfortunately I won't be here, but if you write a midterm test with me, you can use everything except your cell phone and your neighbors. Because in the normal life, you don't need to know everything by heart. So you can check, I expect you to have abilities. You got a problem and you move and somehow fix it. So the ability to fix a problem, that's what I expected you, and not learning the formulas or anything. This is the same what I ask for mathematics or informatics, but I teach you physics right now. Okay, there is some suggested lecture, recommended. You can read it. I think Landau is much better series than Feynman, but well, that's the Soviet superhero and superstar. I learned from that one. Doesn't matter. I provide you the slides, and I will ask only during the exam what is on the slides. In midterm exam, I am troubled because these practices are not meet the expected level, professional level that I usually provide to students. The time is too short. The other time is they are hilarious, so you will have some extra exercises to fix it. I will provide you with the homework. Now I will show you interesting exercises. But those exercises are useful to fix your homework, of course. Okay, where we are? You are expecting mechanics, Newton's law, weight, conservative fields, rigid bodies, oscillations, Fourier transforms. Today I will talk about wave phenomena and one practical aspect, acoustics. However, it has another application, practical application. Oh, not this one, sorry. Physical and wave optics. But to understand this, you have to learn the electromagnetic electrodynamics. But I don't see actually here, that's funny, but I'm pretty sure you will be expert on this. Okay, this is the first slide where I have no acknowledgement for Szilárd and other professors because I wrote perfectly myself. Okay, let's start about some fundamental wave properties. What is wave? You have sine and oscillation, and it propagates. This is the wave. It means a lot of things, actually. If you drop a stone to the lake, then you will see waves moving around and outward. If you take one point, in this point, you will see this oscillating amplitude. But if you made a cross section, then you will also experience periodicity. So wave, a harmonic wave, in either case, are periodic in time and also in space. This equation says the same. You have a sinus, what familiar form. It has an amplitude. It's called amplitude. It's the it gives the maximum minimum value of the sinus. There is some constant and the x coordinate. Here I wrote r because it's radial. And also there is t like time. This is the equation of the wave in one dimension. Because in 2, 3 dimension you also could have this wave equation. Then you should use the magical mathematical objects like Nobla and so on. But I don't want to disturb you and confuse you, so I use the simplest case. There is also a T, that's the initial phase. Just a moment. Okay, I'm logged in. Just the internet is not on its top size. I will send you this Desmos. This Desmos is good for. I don't need. Actually, this is just advice and so. Great, it's me. It's not perfect, but check what I wrote here. Oh, you cannot see. Excellent. So what is here? This is sinus something times x minus something times t. And what I'm playing is the following. This is the, actually it's opposite right now. There is one parameter, which is the spatial periodicity of a sinus wave. And I have this t, and I move it. You see? It's moving. So this is the wave equation. There were very good, very nice differential equation of the harmonic oscillation. Usually we do deduction and got that one, and then we use them. Very often we got this wave equation. For example, now here, you know it. You will cut with electromagnetic waves, and also you can do the same with gravitational waves. You also can do the same in solid state physics, and then you have waves in solid states, in metal or concrete or something like this. This is important for you because you will be electric engineers, and this is something that you always use. Not in this form, but somehow you will use it. Let's return to the slides. Okay, what we have here? This is the equation. This depends from this particular x, the time. There is a constant. This constant is called the wave number. I will return for this. And this is the frequency. This one and the other one modifies the sinus in appropriate state, and this is the phase of the sinus wave. This is the amplitude. The amplitude I will define very soon. This is the maximum extension of the oscillation of the wave. The propagating oscillation is the wave, so it's not so bad. Okay, great. Amplitude. This amplitude A is the maximum displacement of the oscillating quantity from its equilibrium position. Actually, I think that's not trivial. Just learn it. So the maximum is the amplitude. And it gives information about the energy of the wave. Because the energy wave contains energy, impulse, and a lot of things. In next semester, you will learn from quantum mechanics, and in quantum mechanics, since there is something that we call de Broglie, everything which has impulse has a wavelength. But it is for microparticles. Actually, it is good for us. Just the quantities are so weird that it's better to use this classical mechanics that I teach you right now. Okay, mechanical waves. Very simple. I will not kill anyone. This is, for example, a wave. Not a wave. This is a wave. You can see. Sorry, I don't want to assassinate you. That's a dangerous place, actually. Doesn't matter. So, you can have the same in electromagnetic waves. In electromagnetic waves, the electric field became magnetic field, and the magnetic field became electric field, and they propagate this way. You can write down the fundamental laws of electrodynamics and magnetodynamics, and you got the same equation like this one. The difference will be only there will be x, y, z, and d. 4 parameters, not 2. Do you know what is number? Differential operators? Sorry?
Differential operator.
Differential operator, yes. Nobler. Curve, rotation. I think not yet. This is for something that you should learn in third or fourth semester. I learned in my first semester, but I was a physician student. But without it, it's difficult to discuss electrodynamics. Doesn't matter. Now we are in waves. Wavelengths. Let's draw a little bit because this graph is much nicer than my graph. This is a wave. This wave has an amplitude, that's the maximum displacement from the equilibrium position. And from peak to peak, or minimum to minimum, or just zero, well, not this zero, but the other zero, you can take one period, and the length of one period is the wavelength. This is general stuff also, very general. So it's true for a lot of things. Yes, test to test. Yes, test to test. Trough to trough. Okay, I told you I will talk about this constant. This constant is called the wave number, and by definition, this is this 2p per wavelength. Why? This also, it is not written, sorry, I will write this down. This is 2p times frequency. Oh, wait. No, not frequency. 2p per lambda. So this is this provides information about the spatial periodicity of the wave. This is why it is a wave number. If you want to calculate the wavelength, then you just change, so multiply, divide, blah, 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 and got this one. This is not important here right now. It will be important in one slide. Frequency. The frequency, F, is the number of oscillations per unit time. There is one period of time when one oscillation will flow. The opposite is the frequency. Okay? But this is not nice. We use trigonometry and we like radians, and we also like P. So we define this angular frequency. Do you remember from rigid bodies? I told you this will happen again. And this can be got from here. 2p times frequency. Or of course, this is a 2p per capital T. Or you also can get this one. The unit of the frequency is Hertz, named by the famous German physicist. This is also a very nice thing. You know, this physics is not just standing in somewhere in between the spheres. There are economical and cultural influence and boundaries. The names of the different laws are very interesting. First, you start with ancient Greeks. There is no Roman stuff. Then some Italian guy came, then Frenchies, some English, like Newton, some German, and then many Newton comes. And then everything goes to America, and now the new stuff is Chinese, Japanese. It's very important, interesting, which country has such an economical development that can feed the scientists, and also they need these scientists for educating engineers and developing products and new stuffs. That's an interesting stuff, but it's far beyond the scope of this discourse. Now we have the number. We have also the length of these the wavelength. We have angular frequency. There is a very general term. The propagation speed of a wave, electromagnetic wave, sound wave, surface wave on a lake, is nothing more than the wavelength multiplied by the frequency. This is the statement, this will be the result. So, wave propagation speed, I have a wave, and this wave is propagating constant velocity. Then, from this equation, here, I have this formula. I do the difference here, I do a temporal differentiation, then the k is nothing, then x dt, t disappearing, this is also 0. This is the velocity. So if I move this omega, the angular velocity, to the other side and divide by k, I got that v is omega per k. And because the k, the wave number is this one, and the angular velocity is this one, this writing them here, this 2p disappears, and you got this one that we wanted to deduct, we wanted to prove. This is a fundamental wave equation. You have the frequency, you have the wavelength, then you have the speed of the wave. That's important. Okay, and this is what I told you. Okay, summary. The energy of the wave is related to the amplitude. The frequency determines how fast the system oscillates. The wavelength determines the spatial velocity. And the propagation speed are linked to space and spatial and time and temporal behavior. I never mentioned this. Okay. The waves need something, a material or some physical quality, space, time, for example, for gravitational waves, electric and magnetic fields, air or material to propagate. So when you heard that and the T fighters are going, that's bad. In the space, there is no wave, there is no sound, nothing. Only the 2001 Space Odyssey did this. There was no space and voices in the space. Do you know this movie, 2001 Space Odyssey? Have you ever heard about it? But you never seen it. This was made by Arthur C. Clarke. He died in Sri Lanka, Ceylon, a few years ago. He was original, you're correct, electrical engineer. He invented the telecommunications satellite, which are at the geostationary orbit. In that, it is approximately 36,000 kilometers from the center of the Earth, and one period there is 1 day. So if you put something there, it looks staying there. The parabola antennas did the same, and also it's very good for communication.
Movements around the equator, doesn't it?
Yes, yes. There are oscillations and a lot of things, but approximately they are stay there. I will have on 18th of March, I will have a lecture, only one lecture in new space economy. Do you know this new space economy course? So engineers, it will be here in front of us, and then we'll talk about what is geostationary orbit, what are Raunash points, and a lot of things. Okay, so this guy, he also developed radar in the Second World War, and then he became a science fiction writer, and his science fiction was very high quality. So physically, it was everything good. In 1968, with a very famous director, they made this 2001, and that was correct physically. They went to the Jupiter system and did something, and everything was good. Good. There, okay. So this is summary and the wave phenomenon. Propagation. You need propagation material for the wave, for the sound wave or ordinary waves. Very often happens that the wave is reflected. Okay, now it should have a shallow pool radiated, but I don't have that one. But I have the board, and I will provide you reels videos. You have the shore, and there are waves. When they reach the shore, they will bounce back. Okay, this is not good because even worse. I read it first time and you. Okay. So the waves will bounce back from the shore. This is the reflection. Okay, you know reflection from mirrors. It's the same with electromagnetic stuff, but with waves you also have the same. The wave comes, just one, and then it will somehow, the problem is not good. It bounces back. It's not bad. Okay, I will send you later this stuff, but here there are plenty of experiments that I don't find what I need.
Good afternoon, class. In this video,
Okay. Okay, then I cannot find appropriate video. So, oh, I should. If I have this. This is the wave number vector, and these are the waves. Come. So when I draw this one, then you should imagine that waves are coming here and bounce back here. When you will have electromagnetic waves or something similar stuff, then it's easier to imagine. Now these are ordinary waves. Which is important? What is important? If the wave comes and refracted, then the angle between the normal and this angle and the angle between this incoming beam, wave number, incidence, and this is the angle of refraction, and these angles are the same. If you have a mirror and with the light, you know it. I would talk a lot about it. Last time I could not resist and I explained you how the parabola and hyperbola and spherical mirrors are working. This will be the last actually right now. So this is one law about refraction. Very interesting, when they did telescopes, they first did refraction. I will explain what is refraction and not refraction. It's easier to make a mirror than a lens. Doesn't matter. Refraction. This is also general stuff. You have a material. Actually, it could be wave. If, yes, what you don't know, but you don't know that the propagation speed of the surface waves in water is proportional to the depth of the water. So if you have something which is deep, for example 20 centimeters, and there is a wave propagation, and there is something surface, a plane that is only half of its depth, it's 10 centimeters, then the propagation speed changes. And the wave propagation speeds ratio gives a special relation, the refractive index. In glasses and electromagnetic waves in light, you can see that the refraction index is easily visible, for example, in a pool. You look inside, and then everything after the surface changes, and it's difficult to find something below the water because you cannot aim because the way of the light is distorted. This is the refraction. It could be very, very interesting form. If you go to the pool and you look above, then barely nothing you can see, but for example, if you are, not you, there is a fish, a special fish which hunts bees with a glow of water. To targeting from under the water is very difficult, but the fish fix the problem, can calculate this reflection stuff. There is a total reflection. This is a story. If you go to the pool and look, then nothing special about you, but higher reflection, there is a full, the reflection goes to full reflection. It often happens, and if there is an optical experience, it's easy to demonstrate. We will see. Okay, this is a Snell's law, how you can calculate these angles. Great. Huygens-Freshnel principle, that's interesting. If you have a wave, then you can calculate the next wave to assume that in every point of your wave are a spherical wave, and you integrate them. I mean summarize. You know, this snake integral is mainly a summary. Just don't tell to a mathematician, otherwise you know, big pension and a lot of things. I have a good example for this. Actually, something that I have seen. You have a wave with plenty of waves. They are coming. There is a harbor. Then here we will experience such waves. Remember? Every point of the wavefront acts as a source of secondary spherical wavelets, waves. The new wavefront is the envelope of these wavelets. Okay, these waves are coming. They will, of course, reflect here, except here. And this one looks spherical waves. You can check it if you are in a harbor, for example. So this is something practical that you can see in the nature or harbors or something like this. Freshnel, Huygens. There was a space mission to the Saturn, named by Huygens, and Freshnel had some optical elements. If you see this AIKR, you don't jump out of the window, don't you? You know that this is the Euler form of sinus and cosinus. And you also know what are imaginary numbers. Everyone? Yeah. Everyone. Okay. I am familiar in complex numbers and so on. Of course, your second semester, so you know everything. This is something. That's great. If you have, this was a harbor and lake, but now I appointed it as, actually that's not bad, I use the same. So if you have waves, then, and you have a split like this one, actually like so if you have waves, then you will experience here a spot. And this angle is anti-proportional with the size of the split. These for all waves, sound waves, electromagnetic waves, everything. This is called diffraction, and you can also, I must show you because this is not good. Here, there will be bright and dark zones, and you can calculate where they are from fundamental properties of the wave. Here, actually, this is much better plot than I draw. So if the split is wide, then the spread is less. But if it's smaller, then it's spread better. Of course, this is fainter. You can deduct this from this Huygens fractional principle because this period is the starting point of circular wavelengths. And if it's wide, then you expect this shape. When it's smaller, then you expect shape closer to a circle. Is it understandable? Actually, this stuff was not discussed properly when I studied in the secondary school. I learned because only because I was an amateur astronomer. Okay, diffraction. With diffraction of the waves, this is also was topic of another C. Clarke novel. You can make lenses. If you Solar Storm is the title of the novel, and that time Clark was too old, therefore there is another guy who helped him to write the novel. I will write you the title of this novel and you can read it. If you have a plan, metal plan, and you can somehow carve narrow circles in it. It means you carve. So this is metal, the whole blackboard is metal, and this white stuff is carved. And of course, the distance could be much closer than how I drew it. This can form a lens. You can use it as a lens. Focus. Like an optical lens, for example. It is good for light. You can do it with light. But you can do it with other radiation. Protons, high energetic atoms, everything. In the solar storm, ancient hostile civilization made a solar storm, big solar storm on the sun, and want to destroy the human civilization. And the protection is this huge Fresnel lens, and it focuses before the Earth the maximum power of the solar storm, and the civilization is damaged but not destroyed. You should read it. I will send the title. Okay. This is much better. Interference. Interference has some slight connection to resonance, and I have nice picture about it. Here, this is an interference. Here in this one, the two guys made periodic oscillations, and both oscillations creates waves, and some fraction there are increment when the atoms, the waves, the amplitudes are added. Sometimes there is a dissolution when they disappear, when the amplitude are in an opposite phase, and this is a typical interference pattern for surface waves. You will see something similar with the shall I close it? Okay. If you froze or cold, that's made worse my statistics. So, okay. Yes. This is the result. Is the same that you have seen before. I mean here. This one. Almost. This is in space. I drew this myself. Okay, you have yes? You have waves, incoming waves, it's coming, and according to Huygens-Fresnel principle, you have secondary wavelengths. This is a rich university because in Page, my former university, there were no Corot jobs. So enjoy their freedom using them. Of course, they are propagating. So now you have maximum points and minimum points as well. This is a refraction with waves. This plot and that plot are the same. Sorry, you need a little bit check and understand what I'm saying. So there is barrier. There are two splits. The wave comes and made such patterns. And the pattern, in the pattern, the maxima of the interference pattern can be calculated based on this angle and also in the wavelength and also the distance of the splits. Okay. Yeah, it's constructive difference, that's the maxima, destructive, that's the minimum, doesn't matter. This is a quite common stuff. You have seen this at petrol station. You drop some oil, there is a thick layer, and the light refracted from the top, refracted from the other side, and gives this pattern. This is with light and oil. What I just draw, that was with waves. With light, there is a problem. The problem is that in a normal light, there are more wavelength. If you use a coherent source, when monochromatic and coherent, monochromatic means there are only one wavelength, so it's blue or red or whatever, and the coherent means even the phase are the same. The normal name of these waves is laser. I will teach you how to make them in next semester. You need different stuff to do, not simple, but nice. You cannot build a Dead Star, but it's very useful for a lot of things. Okay, here I think that's the best. No, but it's a video, doesn't matter. But you can see how this is for one split actually. This is with two. Two splits. Yes. Just fast. Okay, I'm very slow, so okay, doesn't matter. Yes, polarization. Oh, this is also a very interesting topic. The waves. the waves can propagate what I just go is something like this. It's not in one plane, but everywhere the wave propagates. If you put something, a slot here, then perpendicular to the slot, the wave will not propagate, and only in this direction. It's called polarization, and actually it would be very nice if I would have a PhD student or something else who had done this. If I do this, and it's not enough alone, but if you put two objects with something, then there will be such wave from this one. It's called polarization. The simplest way to happen, for example, on surface of the water. What do you know about insects? They have eyes, but that eye is not like ours. They have multiple eyes. They usually can see the moving, and that's why you cannot kill a fly, because it senses very quickly your moving hands. But they also sense the polarization, and this is how they find the water. However, if there is no water but asphalt, then they are trapped. And also, if the weather is hot and there is a water layer on the asphalt, then also forget this. The asphalt, the melted asphalt, not in natural stuff but on the road, can also trick these guys. The polarization can also help. There are these sunglasses, polar, and it helps. But which is most disturbing? Sorry? Which is most disturbing? The most disturbing stuff, if there is something, a car or anything, and there is a refraction in your eye. But there is also something with the polarization. This is this Malus law. If you have not one, but two slots, and this is fixed, and you can turn this one, then if you change the angle, then the intensity of the wave decreases. You can use this feature to make good sunglasses, for example, or anything else. Or you can determine the polarization of the wave somehow. This is the Malus law. And this plot, is how the electric field, and also there is a magnetic field in this direction, stores the energy, and the wave propagates in this way. Okay, this is really something. I was on holiday, and this is my diary.
So I found the thing you were searching for, the simulation.
You find that one.
Yeah.
Can you send?
It's on to search up wave interference PATT.
Where is it?
Wave interference
Wave interference.
Yeah, PATT.
P
PH
H
E
E
T.
T.
Yeah, that's it. Just search it up.
Mm.
Yeah, the first one.
This one.
First one. This one.
Great, thank you.
No, just the link.
No?
Yeah, press the link, the first link.
This one?
Yeah.
Oh, thank you very much. Thank you so much. Oh, yes, that's nice, thank you. Just how can I start?
Press the button on the tab, yeah.
Here? Oh,
And you have slits too on the bottom.
okay, interference, yeah. Thank you. This is difference. So it doesn't matter. Very nice. Oh, nice.
It's on the top. On the top.
Here.
Yeah.
Yes. The intersection of this is sinus x per x actually. And if you have a telescope the bright stars on a large telescope usually gives this diffraction, this 2. 90% of the energy is there, but you also can see this one, and also you can see the holder of the smaller mirror. Doesn't matter. Okay, I have only 10 minutes or 15 minutes. How much time I have? 20 minutes? 20. Yes. Okay, that will be enough. Thank you very much. I will send this to everyone. Okay, I just told you. So normal. Okay, there is a professor with PhD students and everyone, and have these experiments. They did the experiments. They are more. You can see the videos of what they do. That's normal in a normal condition. I do what I have time. I can provide you the slides and explanation. Now, acoustic comes. I didn't tell you something, and I will add a slide about it. Wave propagation. There are two types of waves. Longitudinal sound, it's like sound waves, and transversal waves. The transversal waves has, for example, this one. That's a transversal wave. Because the oscillation is perpendicular to the wave of propagation. This is good for surface waves, for example. But when I talk to you, there are sound waves. Here, the sound is a compression. The density of the air changes, and this wave propagates the energy, the wave. This is longitudinal propagation. Actually, in 3D, I cannot imagine a transversal propagation, but you understand. So there are two way of energy propagation. Here is explained that. Okay, first of all, sound is a mechanical longitudinal wave that propagates through a material medium due to pressure variations. You need a medium, 2001 Space Odyssey, of course. There is nothing, no no noise of the guys or anything against Star Wars, for example, or any science fiction. There is no propagation in vacuum, of course, and this is caused by oscillation of particles. These are pressure waves, I told you, and here that I wanted to tell you. Here is the propagation, and there is compression, rarefaction, compression, rarefaction. That's the sound. This is how the sound propagates in the air, the water, and also in solid materials. And also plasma. And in plasma, it's a fourth state of the matter. There are other things. The electromagnetic waves are very different, and you don't know what they are, but there, or just in this rope, there is energy propagation, which is where the oscillation are perpendicular to the direction of the propagation. There's the transversal propagation. I will add a slide to explain this one. You have the same equation. I told you so. This sinus kx minus omega minus t equation with some constant will show up many times. It's an important stuff. And the wave speed is similar. So you have a length, you have a frequency. There is a formula, speed, sound, and gases. It is there is this adiabatic index. It is something related to the material and atomic or molecular or other stuff. It would be different. P is the equilibrium pressure, and rho is the density. And at low temperature, usually the sound speed is 343 meters per second. By heart, I know 340 meters per second. Let me tell you what's this. This is approximately 1,200 kilometers per hour. And this is a huge stuff. Leopard 2 Panzerkampfwagen with dry metal gun. Its speed is approximately 1,500 meters. So it's 5 times of the solar speed of the sound speed. The sound speed is also a unit. The waves and fluids and gases behaves different if you are below the sound speed, the flow is below the sound speed, or below. The unit name is Mach. 1 Mach is the speed if the speed is equal to the sound speed. However, there is some problem with this sound speed. For example, if you go to the stratosphere, then the density of the air is much lower than here. It means that the sound speed is much lower than here. So the supersonic fighters, which usually go at 20 kilometer altitude, they can go much faster than this speed, but much faster than the sound speed. But it's not such high than it would be on the surface, because the density of the material is much lower there. You can calculate the same for example, solar wind or other flows, but there is something which is very, very interesting. There is a formula that is not here, but I will find it. Sound speed, yes, it's here. AI, whatever, doesn't matter. No. Yes, actually it's here. So the no, it's not visible. Doesn't matter. What I want to tell you, at Antarctica, there could be minus 80 Celsius. There, the the sun speed is only 270 meters per second. Much lower than here because of the cold. Also, it depends the density, but it also depends the temperature. So that's quite an, I think, important information. Yes, what else can you do with this? Oh, yes. Do you know what are ultrasonic waves? Have you ever had ultrasonic examination? So with ultrasonic waves, you can look in your body. For example, you can check the fetus or your liver or heart or something like this, and it has no consequence. The X-ray examination is some radiation and it's not so good, but ultrasonic is quite good. So yes, there are intra waves. Have you ever heard about infra waves? These are low waves, the human Earth, in theory, can hear from 20 Hertz until 20,000 Hertz. You can hear until 20,000 Hertz. I'm older than you, and I hear until 11,000 Hertz. So if you want to do a Morse with ultrahonk, you can do it. I will not hear it. Some guys did. If you are fatter, then the higher frequency is lower, and if you are older, it's also lower. But what can you do with infrasounds? If the amplitude is high, you can do resonance in your body, and you can tear your heart, liver, tonsils, and everything. Or, with other frequency, you can generate fear, shaking, without any reason. That's the answer of the body for the infrasounds. This is just interesting. What is better? I have a menu, and I have this stuff. Where is it?
This is to break kidney stones as well.
That's ultrasonic, but I will return to ultrasonic very soon. You can do it. You can with ultrasonic stuff. You can break stones or skulls if you want. So it could be a weapon. I will return it. I just mentioned this because that's interesting, and also I need calculator. That's here. Okay. So it's very simple. So the propagation speed is 340 meters per second. So a 20 Hertz ultrasound has 17 meter wavelength. However, if you use an ultrasonic stuff, then the wavelength is 17 millimeters, less than 2 centimeters. The resolution is not so good, so you, if you want to do something better resolution, you have to use higher frequency. So you can calculate easily the wavelength of the sound using the frequency. This is what I wanted to demonstrate, and I just told you why I use these values. Doppler effect. Well, you are standing at the highway, and the guy with the Kawasaki motorbike comes and you heard this one. When something, a wave, a sound, an electromagnetic wave approaches you, then the wavelength is compressed. The frequency, therefore, is higher. This is not a bad thing. I will modify this stuff. Okay, so you are in the this is a surface wave, and you are moving. Oh, I have practiced very soon. So the normal stuff would be this one, but the wavelength, oh, this is a bad plot. I think it's better if I look for an image than draw. Here, that's much better. My daughters can draw very nice stuff, but I cannot ask them to draw Doppler effect or something like this. Here, that's nice. This is normal stuff. There is something, the engine is standing, and you can hear, and the waves propagates. If you are standing here, you are Mr. Observer, Mu, megfigyelő úr in Hungarian, then this is moving, and the sound this will actually record and put it show. Okay. I will go back to this guy, and still the recording is in progress. So you are so the car is approaching, then the wavelength is smaller, the frequency is higher. When it leaves you, then the wavelength is longer, the frequency is lower. This is called Doppler effect, and this is also good for electromagnetic waves. If you can see that a star or a galaxy, they have special lines in the spectra. Doesn't matter what is it. So they in the light, and it is shifted in blue ward or red ward. You can calculate the speed in radial distance, which is very interesting if you check the this Doppler shift for all galaxies which are not bounded gravitationally to our local system, you will experience everywhere redshift. Everything, all galaxy, all part of the universe is extending. It's go further because the material, the space-time is extending. This is cosmology. It's far beyond of this one. The Doppler effect is important. And this is the formula for it. This is the speed of the source. This is the speed of the sun, and this is the speed of the sound. Okay, next one. Sound intensity. It is the square of the distance is anti-proportional with the intensity. You know very well, the first row is empty, so I'm talking very, very loudly, so you can save your earnings if you sit as far as possible from me. I'm just kidding, of course. That's something. Your hearing is not linear. And also it's good for animals and everything. It's logarithmic. Also your eyes are logarithmic because you can look for a moment in the sun and then you can see bright stars at the night. The difference between them is something 8 order of magnitude. 100 million times is the difference. This is your eyes, and also your earrings are also logarithmical, and this is the definition of the decibel scale. There is the intensity, there is a basic intensity, there is the intensity, and you take the logarithm for this. And the unit is decibel. Bell is the bell, the guy. Deci is a small unit itself because it's quite stuff. One interesting stuff, your earrings are more sensitive than your eye. The games with the 16 bits color, it's something 65,000 colors are enjoyable, but if you have the same resolution in the sound, you can feel it's not good. So your hearings are much more sensitive than your eyes. It's actually more ancient. So even it's a long story. And yes, this is a summary. Okay, this is this Weber-Fechner law. I never heard this law with this name, but what I told you, that's the same. Your sensation, your observation is not proportional to the intensity of the sound. The proportional it's proportional with the logarithm of the stimulation, and these are the formulas. Okay, this is good for everything, and that's it. Okay, thank you very much. We'll continue with some practice.